2024 question 5. This is a really good example of why you should always be looking through the entire paper to look for marks, because there are some pretty easy marks at the end of this paper in question number 5 to pick up. So this is some pretty interesting chemistry about the telescopes doing spectroscopy in space, and then we're given this complicated looking reaction scheme for the oxidation of sulfur compounds, and you're given a little bit of information about how to work out oxidation states, which might be the way that you've been taught it, might not be the way that you've been taught it, but it should be fairly straightforward to understand what they're getting at in this paragraph and here. So determine the oxidation states in compounds B, C and E. So we want to do B, C and E. Okay, so let's start with B. So we should have 2 electrons there, 2 electrons there, 2 there, and 4 here. Now, these 4 electrons, they belong to the oxygen. If you don't know what I'm talking about, you need to read this section here before you watch the rest. Okay, so those 4 electrons belong to the oxygen, and then these 6, they all belong to the sulfur, which means that because sulfur originally had 6 electrons and it's still got 6 electrons here, the oxidation state there is 0. For C, well, we know that sulfur is in group 6, so you just treat here sulfur like it's oxygen, so it's going to have 2 lone pairs, and then there's obviously the electrons and the bonds. Now those electrons in both of those bonds belong to sulfur because sulfur's got a higher electronegativity than carbon, so all 8 of those electrons belong to sulfur, which means that it's gained 2 from the original 6 that it had, so the oxidation state there is -2. And then we come to E, which for me is the kind of tricky one, because it appears at first that the 4 electrons here belong to oxygen, 2 electrons here belong to oxygen, and I've got these 2 electrons that belong to sulfur. So if sulfur's only got 2, starting from 6, you'd think it was +4, but this is obviously a bit of an unusual compound because here sulfur is going to have an expanded octet, just like it did down here. All right, and you know, if you want, you can count up all the number of electrons in this entire compound, and you'll see that the only way to get those electrons into that compound is for sulfur to have an expanded octet. So sulfur's got the 2 electrons in the lone pair, and it's got the 2 electrons here, which means that the oxidation state is +2. So we have 0, -2, +2. Then, next question. Compound D can be formed from the reaction of compound C with oxygen. So D is the reaction of C with oxygen. Okay, write an equation for the reaction of compound C with oxygen to form compound D. Well, we don't know what compound D is, so it's probably best if we work out what compound D is first. It's kind of difficult. If I react this with oxygen, I get this, and then this can give me this, and this can give me this. So this has still got my 2 methyls, but it's got 2 oxygens. This has got my 1 methyl and 2 oxygens. I think it's only until you look at this one here that you can realise that obviously compound D must just be that. And then, you know, that's like one oxidation step, and then that's further oxidation, and then that's also further oxidation. But it should be pretty clear that, you know, to go from here to here, to get something from here that can make this and this, it has to be this. All right. So what is the formula of that? The formula of that is C2H6S. Sorry, that's that. C2H6S plus O2 to give me C2H6S O. But I've only got one oxygen, so it's a half there. And then my compound D is what I've just drawn, which is that. Okay. Then, next question. Compound G, right up here in the top right-hand corner, is highly soluble in water, dissolving to form a diprotic acid. I mean, sulfur compounds, diprotic acids, it's going to be H2SO4. All right. And, you know, as we go as we increase along here, the oxidation states are getting ever higher. And you should be familiar with the fact that sulfur here is the highest oxidation state that you can get, right? So here, sulfur is +6. So it makes sense that up here we've got a +6 compound. So compound G is highly soluble in water, dissolving. So how do I get H2SO4? What do I dissolve in water to get H2SO4? We should all know this from the study of acid rain. The SO3 is what I'm going to get there. SO3. Then assume at 323 Kelvin, compound G behaves as an ideal gas. 13.4 centimeters cubed of gas G at 100 kilopascals is dissolved in 1 decimeter cube of water. Calculate the pH. So, what we need to do is we need to work out the moles of, obviously pH is minus log H plus, so I need to work out my H plus concentration. All right, and to do that, I need to work out my moles of H plus. So, and that is going to be equal to 2 times the moles of H2SO4. All right, so, and the moles of H2SO4 is going to be the moles of SO3. Okay, so we want to work out the moles of SO3. Fine. So PV equals nRT. N equals PV over RT. So my pressure is 100 kilopascals. Yep. So it's 100,000 pascals multiplied by the volume, which is 13.4. But we want to do it in meters cubed rather than centimeters cubed. So 10 to the minus 6 to convert from centimeters cubed to meters cubed. R 8.314. And temperature was given as 323. So if I do that calculation, 100,000 times 13.4 times 10 to the minus 6 divided by 8.314 divided by 323 gives me that. Okay, what's that? That's 5 times 10 to the minus 4. All right, now that's my moles of SO3, which is the moles of H2SO4. So I'm going to multiply that by 2. That's by 2. That's my number of moles. I need to do it in a concentration, but it's dissolved in 1 decimeter cubed. So the number of moles is the same as the number of moles a decimeter cubed. So that is my concentration, and then I just do the negative log. And I get a very nice looking answer. Okay, all right, so pH equals 3. Right, pH equals 3. So I feel like this is a fairly straightforward pH calculation question. The direct reaction of compound C with oxygen to form compound D is very slow. In the atmosphere, compound D is formed by a reaction with radical L. So we're now talking about this sort of reaction scheme here. Okay, because they do also ask us about, they ask us about J and N. So radical L can react with C to produce J and N. So radical L produces J and N. Okay, and then we've given this table. So in the answer booklet, tick which of the following descriptions are correct about what happens to compound C during the formation of intermediates J and N. All right, so let's look at N first. So what has happened here? I've gone from, you've got to remember that this thing here is CH3SCH3. And then I've got CH2 radical. So all I've done is I've taken off a hydrogen atom. Okay, so if I write that as a 2, and I've got an H here, and that's got 2 electrons, so I've taken off that, and then I've left behind my CH2 radical. All right, so that is loss of a hydrogen atom. All right, a hydrogen radical. And then over here, the CH3s remain intact, but I've added on an OH, but I've formed a radical. So anytime you have a non-radical species, so an even number of electrons, and you end up with an uneven number of electrons, a radical, you obviously must be adding the radical. So here, this radical has removed the radical, hydrogen atom, to form a radical. Here, the radical is being added on to form a new radical. So this has to be radical addition. All right. Now, the last thing you need to do is you need to go through and double check to see if any of the other things. So it doesn't say, it doesn't say there's only one for each one. So do any of the others apply? Well, I feel like, we can ignore these ones here, and we can ignore these ones here, because if it's addition, it's not substitution, and if it's the loss of a hydrogen atom, it's not going to be the loss of a hydrogen ion. So then it's not going to be atomization. There's no individual atoms being formed. Yeah, I mean, even though you do lose that hydrogen atom, it's not atomization because you are reacting it with the other radical. So we just need to think about reduction and oxidation of the sulfur. So here, the sulfur is bonded to 2 carbons, and here the sulfur is bonded to 2 carbons. So there's no change there. Whereas now, for J, the sulfur is bonded to 2 carbons, but down here it's bonded to 2 carbons and an oxygen. So it's lost electrons. It loses electrons in this bond here. So its oxidation state is changing. All right, so that is going to be oxidation of the sulfur as well. All right, and then give the formula of radical L, I think is probably the easiest question that we can have, because if I have this and I end up with this, it must just be the OH radical. Okay. I'm not sure if radicals, you're probably better off drawing it like that. It's unlikely that the extra electron is going to be on the hydrogen. Anyway, let's not worry about it too much. Then we're going to go on to the last 2 questions, which I think are these are really tricky questions. But let's try and see if we can work out what's going on. So we're given a rate law for the formation of J, which is this one. And it depends on, obviously, C and the L radical. And then we're given some gas phase reaction data. And we're asked to work out the orders of the reaction with respect to C and L. All right, so this is different. You spend 30 seconds looking at this table and working out what it looks like. It's different from the kind of table you might get in an exam or in your class. You only get 2 experiments. So you've got the reactants and you've got the products. Now, if you look for C, in experiment 1, C changes by a tiny amount. So that's not really going to be very helpful, because if you think about how you do this normally in class, you'll be looking for, say, one of the reactants, when it doubles, what happens to the rate? Does the rate double? Does the rate quadruple? Does the rate stay the same? Or if the quantity halves, all right? But here we've got very little difference, except between experiment 1 and experiment 2, where it does half. And experiment 1 for L, experiment 2 is where it doubles, okay? Now, the really tricky part of this question is the fact that you're not given any combination of experiments where the concentration of 1 doesn't change. So between experiment 1 and experiment 2, the initial concentration of C changes. And between experiment 1 and experiment 2, the initial concentration of L also changes. So it's difficult to do an analysis where you're saying, okay, well, experiment 1 and experiment 2, this one stays the same, the other one changes. How does the rate change? So we're going to have to look at something else. And the key thing to realise is that if you look here, the initial concentration of L is 1. After 10 seconds, it's a half. And after 20 seconds, it's 0.25. Constant half-life. If it's constant half-life, it means that L is first order. All right, it's a tricky thing to try and look for, and because when you look at this, you'll be looking for things like if I change the concentration like this, how does the rate change, rather than looking for constant half-lives. All right, then you'll see in the second experiment that the half-life then doubles. So now here the half-life was 10 seconds, so it goes from 1 to 0.5 after 10, 0.5 to 0.25 after another 10, whereas now it goes from 2 to 1 after 20 seconds. All right. So what's the difference between experiment 1 and experiment 2? It is that the concentration of C has halved. All right. So this is the really tricky bit, is that the half-life of L has doubled from experiment 1 to experiment 2. So it's twice as slow. The rate of the reaction is twice as slow because it takes twice as much time for L to be used up by a half. And that happens because of the halving of concentration of C, which means that C must also be first order. All right, now that's the kind of reasoning that you probably won't come across in class, okay? But that is the kind of reasoning that is required here. So if you get it, great. If you don't get it, maybe go back, rewind that bit, and have a little bit of think about it. Then we have the final question. So we are told about this idea that there's an additional molecule that can be involved in the reaction mechanism, and then we're given these two equations. So the rate of the reaction depends on the so for this reaction here, it depends on the N radical and the O2, but that's only when these concentrations are low, whereas actually it depends on all three. Okay, because obviously if N and O2 are really, really low, then the concentration of X probably won't change very much. All right, so which is why it doesn't appear in the rate law, because changing its concentration won't affect the rate of the reaction. But actually X is involved in the reaction, giving us this second rate law. So we need to work out the value of K3. Now, the rate's always going to be the same. It's just the rate constant changes, okay? Because you've got K2 and K3, which means that I can just equate my rate equations. So I can say if I've got rate equals K2 N radical O2 and rate equals K3 N radical O2 X, and those are going to be equal to each other, so I can get K2 N radical O2 equals K3 N radical O2 X. That cancels, and I'm left with K2 equals K3 X. Now I'm asked to find K3, so K3 is K2 divided by my X concentration. Now I'm told in the question what K2 is. It tells me here. K2 is this number, so I'm halfway there. All I need to now know now is the concentration of X, which is a little bit strange because there are two things going on in this question that are a little bit odd. The first one is I'm told here, this hint, the concentration of X is only determined by the total pressure, which is a bit of a strange statement to make. But if we think about it, so PV equals nRT. Now, I'm fixing the temperature at 298, and I'm fixing the pressure at 100 kilopascals. So I can rearrange this equation, R is a constant as well, rearrange this to give me N over V, which is concentration, right? Moles divided by volume, is equal to P over RT. Now, all of these are constant, so essentially N over V is a constant, right? So as long as I keep the pressure and the temperature the same, then adding more moles, I must be increasing the volume, or if I change the volume, it must be done by changing the number of moles. So I see what this is getting at here. It's saying that the concentration of X is only determined by the pressure, all right? Because if I fix the pressure, then my concentration, my moles per volume, must be a constant. All right? And then I have this statement here, which when I did this question sort of made me a little bit confused, because I spent a lot of time thinking, do I need to use this piece of information in my answer to G? All right, and that might catch people out, because they might be thinking to themselves, well, if I can't work out A and B up here, is it something to do with this piece of information? But actually this piece of information is what we need to do this, because this is our concentration of the ideal gas at 298 and 100 kilopascals, which are the quantities that we're given. So really all I need to do is convert 40.4 millimoles per decimeter cubed into molecules per centimeter cubed. Okay, so let's do that. So my concentration of X is 40.4 millimoles per decimeter cubed. All right, and then what I'm going to do is I'm going to convert that into, let's do it one step at a time. So in moles per decimeter cubed is going to be 1,000 times less than that. All right, because obviously this is the number in a, no, hold on. Let's convert it into centimeters cubed first. All right, so this is the number of millimoles in a decimeter cubed. So in a centimeter cubed, I'll have 1,000 times less. So it'll be 0.0404 millimoles per centimeter cubed. All right, because a centimeter cubed is much small, is 1,000 times smaller than decimeter cubed. All right. Now, then, if I've got that many millimoles in a centimeter cubed, how many moles do I have in there? Well, the millimole is much smaller than a mole, so I'm going to have fewer moles. So I'm going to divide it by 1,000 again. So I'm going to get 0.000404 moles per centimeter cubed. All right. Obviously, because a mole is bigger than a millimole, so I'm going to have fewer moles than I will have millimoles. And then I just need to turn it into molecules, which I do by multiplying by Avogadro's number. And I get 2.43 times 10 to the power of 19 molecules per centimeter cubed. Okay, so far so good. Then all I need to do is just work out K3. So K3 is then going to be 5.7 times 10 to the minus 12 divided by 2.43 times 10 to the 19. So 5.7 minus 12. Oh, sorry, just having a bit of trouble using my calculator. I get 2.3 times 10 to the minus 31. Now, rate constants don't have the same units all the time, so we do need to work out what the units of this rate constant are. Now, K2, so K3 is K2 divided by concentration of X. K2 is given as centimeters cubed molecule to the minus 1, seconds to the minus 1, and X is molecules per centimeter cubed. Okay, so that divided by that, but it's a negative, so it's going to be Cm to the power of 6. That divided by that is going to be molecules to the minus 2, seconds to the minus 1. All right, I feel those. Maybe part H not so bad, but part G definitely pretty tricky, but easier in the early parts. Okay, job done.